cool day. And I spoke about Apollo. So next year is the 50th anniversary of the moon landing, right? 50 years ago, wow. And looking around the room, most of you probably weren't born in 1969. So it was quite a long time ago, and there was quite a lot of interest about how people did stuff, because this was way, way back in the past. And originally when I did the talk, it was all about the computer, and then I ran it past a few people, and I realized people don't know much about Apollo, they don't know much about the context. So I kind of took a little bit of the computer out and put a bit more about Apollo and a bit more about the history and a bit more about how they got there. So remember, this is the beginning of the 60s, right? So there's no digital, there's no GIFs, there's no JPEGs. So the stuff that you're going to see, some of it is kind of photostated from books or photostats of books, not the nice normal crisp bus you used to. There was no PowerPoint yet. Okay, so like all good stories, we start at the beginning, and that is the beginning of the space age in 1957. Russia put up the very first man-made object in space called Sputnik. It was about the size of a football, and it did nothing except it had a little radio transmitter in it, and the radio transmitter went beep, 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 beep. And all the little kids went to Scientific American and built little crystal sets. You know, you slide your receiver along the wire, and they could listen to it overhead. And they actually published the schedule of it in the paper, so people could rush outside and watch Sputnik. Wow, this is such a cool thing. So America, obviously, they needed to do something. They were behind in the technology area. So they got an old Atlas rocket, and they decided to launch it.
The launching of the 72-foot missile, a loss of thrust, and fall back to Earth in 6 seconds.
So the papers the next day, you know, had a title like Flopnik, Putnik, all kinds of things which didn't reflect very well on American technology. So, and then finally, in 1961, America finally got a man into space. That's Alan Shepard. He was the first American in space. But actually, when they say man in space, it's kind of like Richard Branson and those guys now. He basically was a human cannibal. They launched him from Canaveral. He went into the Atlantic Ocean, and he just crossed the 200-mile limit, which counts as space, which is exactly what Richard Branson was offering. And then the next guy, Gus Grissom, also did that, and from then on they landed in the Pacific, and they actually went around the world. But at least they've got a man into space, which was a huge technological improvement. But they were way behind on the space race. When Alan Shepard went in Russia, Yuri Gagarin had already orbited the Earth. So Kennedy called his advisors together, and he said, what can we do to beat the Russians? And they said, well, we figure we can put a man on the moon first. So he said, cool. So he went to Congress.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space, and none will be so difficult or expensive to accomplish.
So it was all cool. He'd made this public commitment to America. Unfortunately, he hadn't quite told NASA he was going to say this. So it was a mad scramble. And they didn't, at that stage, they didn't have a lunar module. They didn't know how they were going to land. Lots to figure out by the end of the decade. But what was very, very clear was that they couldn't do it on their own. They needed some kind of computer. Right? There's a whole lot of reasons for that. So one of the reasons is when you're orbiting the moon and you want to come back to Earth, you have to do the burn behind the moon. And behind the moon, there's no radio signal, so your mission control cannot help you. So these guys, it takes 4 days to get to the moon. It's about day 5, day 6. It's going to be a very precise burn, because if you burn too short, you're going to crash into the moon. If you burn too long, you're going to go on your way to Pluto. So they couldn't rely on these guys, because they were pretty tired by then. So they needed something to do very, very precise burns in a very exact time. One of the other reasons is, you can imagine the Earth is the size of a beach ball, and the moon's kind of the size of a baseball, about 15 feet away. The angle that you have to hit the Earth's atmosphere, if you can imagine an A4 piece of paper running horizontally, the thickness of the A4 piece of paper is the angle you have to hit at. You come into sleep, you're going to burn up in the atmosphere. You come into shallow, you're going to bounce off the atmosphere like when you throw a stone across a pond. It's going to be really precise. By that time, they've been in space for 11 days. Again, you can't rely on them to do these really, really complex things. Another reason is orbital mechanics. So when you're in space, you're trying to rendezvous, you're down here, you go up there, and you basically want to catch them up. What do? Well, on Earth, you put your foot on the accelerator. But what happens in space is that going faster breaks gravity. So you actually move outwards, so you've got a bigger circumference. So by speeding up, you actually slow down. So you kind of have to drop down, catch up, and then rendezvous like that. And in every single time the NASA guys tried to rendezvous without some kind of computer, they failed dismally. So you needed some kind of thing to help them, some kind of fly-by-wire that's really going to do the difficult stuff for them. So that's cool, no problem, we'll get onto Radio Shack. Okay, that's generally recognized as the very first, what we call a PC. And you can see from the dates, 1974, so that's 14 years in the future, right? Clearly you can't do that. And the PC, they came out in 1981. So the only choice they had was they had to build it themselves. But remember, there's no integrated circuits, there's no EEPROMs, there's nothing. There's no hard drives, there's no solid state drives. And clearly you couldn't take the NASA mainframe, which is a Honeywell 800, and put that into a space. It's a little bit too big. So they went to MIT, and they asked MIT to write the software for this thing that they hadn't built yet. And they actually didn't know how it was going to be built. And they had no idea what the requirements were, because they'd never done this before. They chose MIT because MIT had developed the inertial guidance system for a Polaris missile. Polaris missiles are the ones you fire from submarines. And you can see the wording of this massive contract. It didn't have any requirements because no one had a clue what it had to do. It's just like, do the stuff when we figure out what that stuff is. Okay, so that's what the Apollo guidance computer looks like. Right? It's a little box, and it's got a little display keyboard on the right-hand side. There was one of them in the lunar module, and there was one of them in the command and service module. So there were two, but they're in two different pieces of software. So obviously, the function of the two is completely different. Those are some of the things that it needed to handle. So you can see it needs to handle where it is in space. It needs to handle inputs from the gyroscopes. It needs to handle the astronauts moving the joysticks. It needs to handle telemetry, get signals from Earth. And when I say telemetry, the guys in mission control, they weren't using Power BI, right? What they saw was a long sequence of numbers. And they knew from practice that this sequence of numbers looks good, and that sequence of numbers looks bad. They're literally just a stream of numbers going across the screen. That was the telemetry. But you can see there's a whole pile of stuff that this computer has to take care of. Basically, enabling them to fly through space in 3 dimensions, 250,000 miles to the moon. There's another schematic. You need to take inputs from the astronauts. You need to give engine commands. You need to get the gyroscopic settings, and so on. So it's got a lot of stuff that it has to cope with. When they were in space, of course, it's drifting off slightly. So what they did is they had a guy using a sextant. They chose 6 stars that they could see. And they took sextant readings on all 6. And then they typed those sextant readings into the computer using that DSKY, which you'll look at a little bit later. And then the computer from those settings would calibrate where it thought it was and where it actually was, and it would adjust so that it was, in exactly the right place, because obviously it's quite a complex navigation exercise. That is in the lunar module, a really simple little device. Basically, when you were landing, you looked through along that gauge and you saw the number. You asked the guidance computer, what number are you aiming for? And you looked through on that number, and that would give you the landing point. If you didn't like that, you could move your head up and down across the scale, and you could say, well, that looks like a nice landing place, and you tell the computer to rather go there, and it would adjust its trajectory to land at that point. So, of course, number one thing, how do you get the code into the computer? Again, there's no memory, there's no solid state, there's no drives. So what they came up with is a thing called rote memory.
Margaret Hamilton was one of the very few female engineers on the project.
The rope is made up of rings and wires. And if the wire goes through the core, it represents a 1, and around the core, it represents a 0.
It was extremely slow. One program could take several months to weave, and if there was an error, it was a nightmare to correct. The software program was falling dangerously behind schedule.
So you can imagine that, right? You write the code, you've got to compile it and assemble it into the bits. And then you have to weave that for every single bit. None of this CI/CD stuff. And you couldn't make a mistake because you couldn't realize halfway through there was a bug. You had to start all over again. Not a good idea. So they had to put really a massive amount of effort to making sure they had the damn thing right before they sent it to these ladies. These ladies were highly skilled. They were paid really good salaries because literally the lives of the astronauts depended on them weaving the stuff properly. If the program worked and they weaved it wrong, it wasn't going to fly. So some stats. It had a whole massive 5 interrupts. It had a 1 megahertz clock, 16-bit words, 2K of RAM, right? 2K. 36 words of ROM. There were actually 32 words as opposed to you can address with 16 bits. But they had one 4K segment that they used as bank memory, so you could swap one 4K segment in and out. And again, you have to be very careful that that 4K segment, the code stayed within that segment. You couldn't jump to another segment because, of course, that segment wasn't loaded. So again, a whole lot of stuff they had to check out manually. It drew 55 watts, and luckily, at about the same time as we were trying to build this thing, Fairchild Semiconductor came out with this magic new thing that they called an integrated circuit. Very first integrated circuit. And NASA decided to bet the farm on these things. No one else had ever used them. The problem with Fairchild was that they weren't going to make them unless they had a guaranteed person to deliver to, a guaranteed order. So NASA contracted to buy 60% of their production. Not because they needed it, but that's what Fairchild wanted in order to keep making it. And you can see that it was a full decade before a really commercially available one came out, and that one was only 4 bit. Okay, so words are 16 bits long. As always, you have a parity bit. So that gives you 3 bits for the opcode. So if you know your octal 3 bits, it's 8 instructions. Not a whole lot of instructions. Sometimes the instructions didn't need the full 16 bits, and they could use a little bit more for some other instructions, and there was a thing in the code that didn't extend. They didn't really have an operating system, right? They had a very simple queue management system. When interrupts came in, they put them into a queue ordered on priority, and that told the processor what to do next. Basically, there was a wait list, and every now and then they saved the current state of the system because that allowed them to restart it. So because the code was in the memory and the code were the same thing, you could restart instantaneously. So that was one big advantage of this road memory. You didn't have to worry about disk crashes or anything like that because there was none of that stuff. Basically, it couldn't be simpler. Unfortunately, they very quickly realized, especially when it comes to vector and scalar arithmetic, that 8 instructions were nowhere near enough. So they developed this concept of interpreters. So they wrote instructions that decoded other instructions, just like VM works or Java works. And that allowed them pretty much to do anything they wanted. But of course, it's a whole lot slower than actually writing code that runs directly on the CPU. But that allowed them essentially to have as many new commands as they needed for whatever functionality they were going to develop. They had 2 basic data sets. So they had a core set, which was the basic one, which the code used. And if that overflowed, you got a 1202 alarm. And then they had another one which stored up all the vital bits of the interpreter code that was running at that point. And if that overflowed, you got a 1201 alarm. Okay. So that is the key input and output. So that's like the very first example, really, of UX UI. It had some lights on the left that basically told you the status of various things. And then it had lines of displays on the right that showed you what noun you were running, what verb you were running, the kind of status of different parts of memory. And down the bottom, you can see you can input verbs and nouns, I'll explain that, and you can run a certain program. So they had lots and lots and lots of subroutines, and they started from 00, and I think they went up to about 78. And so you could tell this thing to run program 64, which was landing on the moon, and program 65, which was taking off, if I remember. And then, if anything went wrong, the lights flashed, and that was it. That was the interface that the astronauts had to push to get this thing to do what they wanted it to do. And you can see there that that's where it sat in the lunar module, right down the bottom in the center. And both the pilot and the commander, Neil Armstrong and Buzz Aldrin, could see what was going on, and both could push the buttons. But only Neil Armstrong, who was the pilot, actually flew it. Buzz Aldrin's job was really to monitor it and call out all the settings so that Neil Armstrong could concentrate on flying it. Okay, that's it in a little bit more detail. You can see there's lights to show all the different states. There's some examples of what was shown. You can see it's doing verb 39. And you can see there's a whole lot of displays here. So those displays varied on what programs you were running and what keys you pressed. It's really pretty basic. I mean, you couldn't really have made it a lot simpler than that. So the code is all on GitHub. Someone actually took a source copy home, and I'll show you what it looked like. And someone actually literally transcribed it. It's all on GitHub if you want to go and look at it. And in the middle of it, there's a quotation from Shakespeare about nouns and verbs, which is quite interesting because there was no Googling to go and search for stuff. So someone must have known Shakespeare pretty well to figure out that part referred to nouns and verbs. So nouns and verbs were how you told it what to do and what to do with, within that kind of a subcategory. So, for example, verb 50 is please perform, and verb 51 is please mark. They had lots and lots of these things. Basically, this is what you have to do, and then I'll tell you exactly what the parameters are for that in the nouns. So, for example, 09 is alarm codes. I don't know what all those ones did, but you can kind of see how it fitted together. So, verb 37, then you push the select. At 63, verb 5, noun enter meant display the program along, because you saw on the previous one, 9 means display program along. So if you did see some kind of program alarm light come on, you could enter that in to see exactly what the program alarm was and what it meant. Okay, so they've kind of got the computer, and they've kind of worked out how the hardware works, but they still have to build the software. But remember, there's no PCs, right? There's no ReSharper, there's no Visual Studio. There's basically nothing. So how did they actually build the software? Okay, there was no text editors, no assemblers. Basically, everything that they did, they had to build from scratch. And the way you do it is you do a cross-compiler. So that's where you run a code on one machine that produces assembly code for another machine. So they ran the code on that mainframe that I showed you. It's probably written in COBOL or Fortran or something, and it wrote out the instruction codes for the CPU in the guidance computer. So how did it work? Well, cool. You go and assemble the code on the mainframe, except the mainframe ran out of memory. Oh, well, so a bit of trial and error and work out. The mainframe can only handle 20% of the code. So you put in 20% of the code and you compile it and you write it to a tape. And the next 20% you write it to another file on the tape. And you do it 5 times, so now you've got 5 files on the tape. Then you read the first file, you take the 5 files and you concatenate them to one file on another tape. And then you run another program to take the assembly, to convert it into binary, which is the ones and the zeros, and that's what you send to those ladies who weave the rope. Right, so this is not a little right-click publish kind of thing. This is a pain in the arse. And if you got anything wrong, you had to do the whole damn thing again. Okay, so that's kind of how they got the code into it. So there's an example of assembler code. So if lock counters at address 1200, the machine code would be 06, and that would translate down the bottom to the binary, and that's what gets woven into the rope, those ones and zeros. Okay, that is a code in the listing for a 1202 alarm. Remember, the 1202 was when the core set overflowed. And you can see there's a clear and add fixed, whatever's the contents of core ink into the accumulator. You can add some stuff to storage. And then they've got a command called CCS, count, compare, and skip. And that basically says, take the next branch if it's greater than, the next branch if it's equal, and the next branch if it's less than. So it did all kinds of stuff, and you can see there's the 1202 octet. So that's an example of the assembler code that they had to write. That's an example of the interpreter code. Now, I know what these guys were smoking when they wrote this code, because you can see the comments about Dionysian flag, and Dionysius is the god of the grape harvest, and madness and ecstasy, and God knows what else. So that's basically something that just goes around clearing a whole lot of flags. All right, so how did you actually write the code? Okay, remember again, there's no Visual Studio. So what you used is that, and that is a coding sheet. Right? And I see some people smiling because they've probably seen one of these. It's 80 columns long because that's how long a punch card is. First 6 columns are for the sequence number. If there's something in column 7, it's a comment. Then you've got from column 8 to column 72, if I remember. So you put your code, and then there was something else in 73 to 80. So what you did is you took that, and you took your pencil, and you wrote the code. And that's what it looks like if you write the code. And that's COBOL, right? Some people might recognize it. So now you've got a piece of paper with the code on it. Cool, that's a start. And that's what a punch card looks like. So one punch card, one line of code. And then what you did is you took that nice little coding sheet and you sent it up to some ladies upstairs who used this thing called a card punch. So they had a whole stack of damn blank cards in the left-hand hopper, came down one by one, and they went over here and they typed in what you'd written. If you'd written something wrong, well, it got typed wrong. Okay. So it had to be really, these guys must have had really good handwriting because they had to read this stuff. And then it went to another lady who flicked one of the switches on the actual typewriter there, and it became a verifier. So you typed the same thing, but didn't actually punch the cards. It just verified that what the woman had punched was actually what was on the coding sheet. And then that was sent back to you in a nice big deck of cards with a rubber band around it. And then you wrote a whole JCL, which is job control language, to tell the computer what to do with this deck of cards, because the computer hasn't got an idea. It just knows it's a deck of cards. And you send it up to the operator. So this is all batch, right? Everyone had a little letterbox, and they put this stuff in the letterbox, and then the operators ran it. And 4 hours later, you'd come and get your printout. Then you do it again if you had a compile error or something. All right? And that's what read them. Right? They took their big set of cards into a card reader, and it whipped them through one at a time, and basically put it into memory, compiled it, all that magic stuff, and then it printed it on a printer. It's a mechanical printer. You can see the papers joined together. You can see it's got sprocket holes on the right and the left because these sprockets to pull it through the printer, right? And that is the listing of Luminary. That's where the coding GitHub comes from. So Luminary is the lunar module code for Apollo 11. And that was your code, right? So there was no magic search and find reference and all those kind of things. You had to look through the listing, which was probably not easy when you've got a listing that size. Okay, that is a deck of cards in a card box. That's how you walk. So we've got a new name for that today. Today we call that GitHub, because that is your code repository. Right? And if you're wondering about the diagonal lines on the cards, that's so that if you drop the damn cards, you can sort of put them back in the right order. So dropping the cards is not a good idea. Dropping the box is somewhat short of a catastrophe. Okay, so you put diagonal lines so you could kind of match them up. Fun and games, right? And that was the code repository. So you probably had version 1, version 2, and they're all stacked up in a cupboard somewhere. That's Margaret Hamilton. She was one of the program managers. So you saw earlier when she was telling you about how they did the rope memory. So you can see after a while, you don't need the yellow pages to put your monitors on. You just use all these printouts. And the office is just full of all these printouts. And it must have been a nightmare to find the right version. Cool. So been through the hardware, how the code got loaded, how you wrote the code. So I'm just going to tell you a little bit about the mission so that you kind of understand what happened. So that's the bottom of a Saturn V rocket. So the Saturn V rocket, really big, massive thing, probably the most advanced thing anyone ever built at that point. It had over 1 million moving parts, really complex. And the bottom part was really just to get you off the Earth, right? So the bottom part was just a whole lot of disposable stages just to get you away from gravity. Because that's the big problem. The more interesting stuff is in the top part. So we've got the lunar module, which is attached inside one of the stages. And on top of that, we've got the command and service module, which is basically where all the electronics is. And on top of that is the command module. So that's where the astronauts sit. And then there's an escape hatch, which blew off just after they launched. And I don't think they ever used it, probably luckily, because I reckon it would have probably killed them. It was never actually tested in real life, thank God. And the command and service module, that whole huge stack, which is this massive rocket, and you've seen pictures of it, that's the only piece that came back to it. From that whole rocket, that's what came. So they launched the rocket. The command and service module, they turned around and they rendezvoused with one of the stages and they pulled out the lunar module. So now you've got the lunar module and the command and service module all together, ready to go to the moon. And then you go to the moon and you separate, command and service module keeps orbiting, lunar module lands, right? And then the top half of the lunar module blows off. So the bottom half stays with the legs. The top half, which is just enough for the guys to get back to the command and service module, is what takes off from the moon. And then it comes up to the command and service module and they rendezvous. The astronauts walk in to the command and service module. They take all the moon rocks with them because that's like really important. That's why they're there. And then they let that half of the lunar module go and they program it to crash into the moon. Because what they did on the moon is they set all these experiments and they wanted to see what kind of tremors they get and what kind of readings. And then that comes back, gets down to Earth and then lands. So you can see just a little piece at the bottom is what lands on the Earth. And lands in the sea. There was an aircraft carrier next to it. Pick them up by helicopter. Job done. It took 11 days. So 11 days in a thing, it's literally like 3 chairs put together and a little bit of space in the CSM. Probably wasn't a whole lot of fun. Okay, so mission control. So all these specialists, the way that NASA worked is they tried to anticipate every single thing that could happen, and they wrote the rules for it. So to land on the moon, you have to have the following things. If this happens, this is what we're going to do. And they did it like that so that they don't have any arguments. Like, these are the procedures we're going to follow. If it's in the book, you follow the book. You don't get a choice. They had a guy called the flight controller, and what they figured out after a while, flight controller is God, right? Because he can't go and ask people. You've got a crisis, you've got to deal with it. He makes the call. He doesn't have to worry about NASA management. He doesn't have to worry about anyone else. He's in the hot seat. He makes the calls. To help him, he's got all these specialists in front of him. So the guys we're going to be looking at is the guidance guy, the Capcom guy. The astronauts wanted an astronaut to speak to them in space. So the astronauts could not hear what was happening in the mission control. It was the guy in mission control speaking to the astronauts who kind of gave them the commands. And of course, you had the flight director, who was God, basically. And the rule was that in any situation, if you owned it, if you were the expert in that, you had 20 seconds to make a decision. That's it, 20 seconds. You've got to decide very simply, go, no go. You don't get more time. You just got to have to go. You've got a back room of people behind you. They had all these little communication loops. You could speak to the guys on the loop. You could speak to your back room. You could get some input. But you only had 20 seconds to do it. Because they have crises, right? You need to resolve. Okay, and that's what mission control looks like in real life. And so those are the guys I'm going to talk to you about. So we've got Gene Kranz. So Gene Kranz also happens to be flight for Apollo 13. If you've seen the movie, he's the guy who says failure is not an option. Actually, he never said that. The scriptwriter wrote it. But he loved it so much, he called his book, Failure is Not an Option. You've got Steve Bales, I think, was 24 years old. He's the guy. He's in charge of the Apollo flight school. These guys got paid peanuts, really. They got paid nothing. But, you know, the chance to put a man on the moon, wow. These backroom guys, a guy called Jack Garman, and the Capcom was Charlie Duke, who actually went to the moon in Apollo 16, if I remember correctly. Okay, so we're 30,000 feet up, Apollo computers, handling things, everything's a dream. If you look at the bottom, you'll see a little curve that becomes a bit bigger. That's the moon.
You're looking at Ariel 3. That's perfect. Put in one. Looking good, over. Apollo 2. 1202. Good radar data, altitude now 33,500 feet. Give us a reading on the 12.
Sorry. What happened? Sorry about that. Why is it not playing?
You're looking at RLD. That's affirmative. Program one. Looking good, over. So 1202. 1202. Good radar data, altitude now 33,500 feet. Give us a reading on the 1202 program alarm. Roger, we're going at alarm. Roger, 330. 6 plus 25, throttle down. That is 25, throttle down. Roger, copy. 6 plus 25. We're still go, altitude 27,000 feet. Same alarm, and it appears to come up when we have a 1668 up. Roger, copy.
Okay, so nice smooth mission. Suddenly, 1202 alarm. No one in mission control, apart from I think 2 people, actually knew there was such a thing as a 1202. So at that point, right, most people in mission control thought that's the end of the moon mission. Remember, the whole world is watching this, right? This is the biggest television audience in history, biggest radio audience in history, people listening to Voice of America. 1202, Steve Bales, right, that dude. 20 seconds to make his mind up, and he's never heard of a program. So the mantra is, if in doubt, bail out, just say no go. So he's sitting there, right? It's a very close-knit community. He knows all the astronauts. He knows their wives. He knows their kids. Doesn't want the guy to say go and the damn thing crashes, right? Worse than that, maybe, there's a dude in the White House called Nixon. And Nixon is not a fan of the space program. Nixon wants to cut it. One of the reasons he wants to cut it is because there's this other little venture that he needs some money for called the Vietnam War. He's waiting in the White House to make a call to the astronauts when they land on the moon. This is going to be the first American president speaking to a citizen on another orbital body. Right? He's got huge publicity around this, and he's got this like he's trying. He's not a fan, but he pretends, well done, you know, I'm the guy who made it happen. Well, typical politician. And all this stuff's going through Steve Bales' head, right? He's got Jack Garman in the back on the loop. Jack Garman has seen a program. Jack Garman asked MIT what to do, and they said, if it's still flying and if the telemetry is still good, all it's going to do is it's going to reset instantaneously, and it's just going to keep on flying. So if it's doing all those things, ignore the alarm. So he sits there, and he says, you heard. Suddenly you hear Neil Armstrong. Neil Armstrong says, give me a reading on that 1202. I like the guys that are nice and safe and sound and warm in mission control. Neil Armstrong's on his way to the moon, right? He doesn't know if he's about to crash and burn. He doesn't know if he's about to crash. He wants a reading. What the hell is going on, people? And so Steve Bales makes the call. He says, go. He's summed it up. Telemetry's good. Computer's still working. Everything's fine. We go. All right? Capcom tells him we go. The whole of mission control is just going, oh shit. This is probably not the decision we were expecting. A few seconds later, you hear that 1201 interpreter overload. Now he's rolled the dice, hit one, right? He's hit the jackpot. Straight away, he says we go same time. On the way to the moon, having never seen a program alarm, there were 5 program alarms. And he just said, go, 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 go. They landed on the moon, and you hear those famous words, Houston, Tranquility Base here. The Eagle has landed. And mission control goes completely apeshit. America goes apeshit. There's people running around with flags because they've landed a man on the moon and they've won the space race. But why? Why, after nothing, did they get all these alarms? And this is one of those things where, you know, that one little change is not going to make a difference. So Buzz Aldrin is one of the astronauts, and he is petrified that when they're coming down to the moon and they have to abort, he's not going to be able to find CSM, right? So he says, well, on our way down to the moon, can we turn on the ascent radar? So this has got nothing to do with descent. So they can keep tracking where the CSM is and have a quick meeting. Yeah, that's not going to cause any problems. And so the computer is handling all the stuff from the descent, and suddenly it's getting all these interrupts from a radar signal that it's not even programmed to handle. And so what does it do? It just keeps resetting. That's how it's designed. It just keeps resetting and keeps on flying. So you can imagine on Apollo 12, they didn't have it on. And Apollo lands on the moon and all is cool. And it comes home very safely and they're all heroes and they go on round the world tours and things. But the computer did its job, right? Just kept them flying. Okay, so we jump now to Apollo 14. So Apollo 14, the commander was Alan Shepard, who was the guy that you saw in that picture. First man in space. So Alan Shepard, same thing, coming down, and suddenly mission control notices that the abort switch is on. And what happens if the abort switch is on is once it gets to 24,000 feet or something, the computer blows the two apart, so you can't land on the moon because you don't have any legs. That's the end of the mission. And so apparently there was a bit of solder behind the switch or something. The switch wasn't actually on, but the computer thought the switch was on. So that was. So in a blind panic, NASA phones MIT. The guy's name was Don Iles, and they say, we have a problem. You have to do a quick patch to tell the computer to ignore the abort switch. So that's all cool, right? Yeah, no problem. Here's the bad news. You've got 90 minutes. So why 90 minutes? Well, first of all, very tight time frame for the mission, so don't have an extra hour and a half. Secondly, you're using oxygen, right? There's a limited amount of oxygen in the lunar module. And that's another hour and a half worth. But the most important thing is because the moon, it's a featureless landscape. Right? There's no features. Here on Earth, you can see an object, you can see a tree. Rough idea how the object scales to the tree. On the moon, there's nothing. Big boulder, little boulder. You can see, yes, that's smaller, but you've got no idea of the size of them. So the way they got around it is they landed just when the sun was coming over the horizon, because what that does is it throws shadows. And you can see lots of shadows here, bad place to land. Not a lot of shadows over here, probably not a lot of rocks here, you're going to land over there. And of course the sun is not static, right? So they had 90 minutes before they went over. Remember I said they had all these things about when you could land, 90 minutes was their margin. So you had 90 minutes, not just to work out the fix, to take it to the simulator, to test it, to write out the code, to compile it into the bits and bytes, and then call it up to the computer so the guy could go to the Dusky and type it in. 90 minutes. Wow. And of course, America's watching. Right? This is Apollo 14 and Alan Shepard. He's a national hero. Okay, so he did it. He worked it out. But we had to turn off the program alarm. So basically, he goes types verb 21 noun 1, load full word. 1010 is the address of the flags register. 107, turn a thing on or off or whatever. 65 keystrokes, right? So Capcom gets this piece of paper. So read this out to the astronauts. And the astronauts are standing there, zooming around the moon, pushing this button and just praying that they don't get it wrong. But it worked. Apollo 14 landed on the moon. So I just think like this guy is probably asleep on a sofa thinking he's going home and suddenly 90 minutes in the show. It's like, whoa, take my hat off to that guy. Okay, so they made 75 of them, and they cost about $200,000, which is about $1.5 million in today's terms. To help 12 men land on the moon, right? Because Apollo 13 didn't land on the moon. And Nixon, in his genius, cancelled Apollo 20, Apollo 19, and Apollo 18. So only 12 guys. It played a major part in the recovery of Apollo 13 because it actually stored all the guidance stuff. So they moved it up as much as they could to the lunar module and then they moved it back again. And it never crashed, not once. No failure. 1972, Gene Cernan, Apollo 17 blasts off from the moon. And that's the end of the Apollo missions. Sadly, we've never been back, although Donald Trump apparently is going to start a new military branch that's going to be space cadets. And we says we're going back to the moon, so who knows? Okay, so some of the references. If you go to the virtual AGC page, someone has actually written an assembler to take that code and some, you know, they've got a thing, you wrote the AGC, it runs in a VM in Linux, and you can actually play with it, push stuff. It's all quite magic. The only problem is, of course, it doesn't do anything because it's programmed to get all these inputs, which the inputs aren't there. There's no gyroscope, there's no telemetry, there's nothing. But you can go and have a play with it if you want, and all the code is there. There's quite a lot of stuff left from MIT in direct comparison, because there was another computer in the bottom of the Saturn V that handled the engines. That was done by IBM, and that code has disappeared. Yeah, a lot of stuff there. And that's it. Thank you.